everyone, I'm Professor Harrison, and welcome back to our module on probability for finance. Today we're going to learn how to work with a normal distribution table and how to turn a z-score into a probability that we can actually use. We're following Danny, a gambler with a mountain of debt working his way through a box of mysterious letters addressed to his late father, trying to understand what happened to his family fortune. Today he's trying to calculate the probability that he can actually pay off what he owes, and it turns out that turning to one of those mysterious letters is exactly what he needs. We already know that for any normal random variable x, we can calculate a z-score, x minus its mean divided by the standard deviation. That tells you how many standard deviations above or below the mean a particular value will fall. The normal table converts that z-score into a probability. The table we use only covers positive z-scores, and here's the key thing to understand about how it's set up. For a positive z-score, the table gives you the probability of falling above that value, the right tail area. That ends up being the smaller number. If you want the larger chunk to the left, you have to use the complement. For a negative z-score, you look up the absolute value in the same table. Because the normal distribution is perfectly symmetrical around 0, the area above positive z is identical to the area below negative z. So looking up the absolute value of a negative z-score gives you the left tail probability directly, no extra step needed. In other words, the table always hands you the smaller outer tail. The complement gives you the bigger piece. So how do we actually read this table? Well, the table's organized around the z-score's decimal places. The row labels carry the z-score through the first decimal, so you'll see rows labeled 0.0, 0.1, 0.2, and so on. The column labels carry the second decimal, 0.00, 0.01, 0.02, all the way up to 0.09. To look up a z-score, you split it at the first decimal place. The part through the first decimal tells you the row, and the second decimal tells you the column. Go to that row, slide across to that column, and that number tells you your tail probability. For example, suppose z equals 0.71. The first decimal gives you 0.7, that's your row. The second decimal is then 1, that's the column labeled 0.01. Go to row 0.7, move across to column 0.01, and you end up at 0.2389. So the probability of falling above z equals 0.71 is 0.2389, or about 24% of outcomes will fall above that value. If you wanted the probability of falling below 0.71, the bigger chunk, you apply the complement rule. So 1 minus 0.2389 equals 0.7611. About 76% of outcomes fall below z equals 0.71. Now suppose z is a negative number. For example, let's use negative 1.43. We take the absolute value at 1.43, and then we look that up in the table to get the left side of the distribution from this z-score. So the row here is 1.4, the column is 0.03, and that cell gives us 0.0764. Because of symmetry, the area above positive 1.43 equals the area below negative 1.43. So the probability of falling below negative 1.43 is 0.0764, about 7.6%. The table handed it to you directly once you use the absolute value. If you want the bigger chunk, the probability of being above negative 1.43, that's the complement rule. So again, 1 minus 0.0764 equals 0.9236. About 92% of outcomes will fall above that value. Here's how this plays out in a real-world problem. A bond portfolio has an expected quarterly return of 3% and a quarterly volatility of 5%. What is the probability the portfolio loses more than 3% in a given quarter? We need the probability that the return x falls below negative 3%, where x is normal with mean 0.03 and standard deviation 0.05. First, we standardize. Z equals negative 0.03 minus 0.03, all divided by 0.05. That's the negative 0.06 divided by 0.05, which gives us exactly negative 1.2. The z-score is negative, so take the absolute value, 1.2, the row is 1.2, the column is 0.0, that cell gives us 0.1151. By symmetry, that's the left tail probability directly, the probability of falling below negative 1.2. So there's about an 11.5% chance the portfolio ends up losing more than 3% in a given quarter, roughly 1 in every 9 quarters. No complement needed here because the question asks directly for the small outer tail. Sometimes the question runs backwards. Instead of what is the probability of falling below this threshold, You want to know what threshold corresponds to a given probability. To do this, we just use the table in reverse. We scan the body of the table for the tail probability that we want, and then we read off the z-score off the row and column labels. Suppose you want to find the return level such that there's only a 1% chance of doing worse than that in any quarter. You need a threshold in the left tail so the z-score will be negative. A 1% left tail probability corresponds to a 1% right tail probability on the positive side. So you scan the table for a cell close to 0.01. You'll find it around row 2.3, column 0.03, which gives us a z-score equal to positive 2.33. Since this was the left tail threshold, the answer is negative 2.33. Now we can convert back to actual percentages. We can do so just using the z-score formula. X equals mu plus z times sigma. That's 0.03 plus negative 2.33 times 0.05, which gives approximately negative 8.65%. So there's a 1 in 100 chance that the portfolio loses more than 8.65% in a given quarter. That is what a 1% quarterly value at risk actually means. Danny puts down the letter. He has a number he's been carrying around for months, the total amount he needs to pay off his debt. He also has a rough estimate of his monthly income going forward and a sense of how much that income varies month to month. He sets it up the same way. He uses the last couple months of data to calculate his monthly expected value and standard deviation of his savings. The question is whether those numbers can realistically get him to zero within 18 months. He standardizes and finds that the z-score is negative. He takes the absolute value, finds the row, finds the column, and reads the cell. The probability isn't high, around 23%. He sits with that for a moment, then he goes back and changes one number, his expected monthly surplus, assuming he cuts one significant expense he's been avoiding cutting, and he runs it again. The probability jumps to 41%. It's not great, but it's the first time he's thought about this probability rather than a hope. That turns out to be a little bit different. So that's how you work with the normal distribution table. The table only covers positive z-scores and it gives you the small outer tail. The area above for a positive z-score, or equivalently the area below for the corresponding negative z-score by symmetry. Take the absolute value of your z, find the row using the first decimal, find the column using the second decimal, and read the cell. If you want the bigger chunk on the other side, then we can just apply the complement rule. And if you need to go in reverse, finding the z-score that corresponds to a given tail probability, then you just scan the table body and read the coordinates back out. That process ends up being the foundation for everything from portfolio loss calculations to value at risk.